Okay, hi everyone. Welcome back. This is going to be the video for the practice exam 3 walkthrough. So essentially what we did, the same thing what we did for midterm 2. Uh, it's under the assumption that you've already completed the practice exam in the way that I suggested you to. So I'm told you guys to study and then take this practice exam as if you were in a real exam setting, so closed book in 60 minutes, to see how you actually do in a setting and see if the test is going to be paced well for you and if there's any room for improvement anywhere. You can check using this study tool. So yeah, so the you can either now go through the solution manual, see where you missed, or you can watch this video here, where we go through the practice exam in whole in real time. And again, I would like to remind you, if you do well here, it's going to be good because this practice exam is in the exact format of what you will see on Tuesday the 18th, right? This is essentially going to be what you would expect. I just changed a few numbers around um, to, of course, not make it completely one for one. But if you do well here, then you should be in good shape for the exam. Okay, so let's begin. All right, so in problem one, I give you a function p of x in factored form, and I ask a few things about it. Notice that p of x has the first factor x squared minus 9, so we can expand that out using difference of squares as x plus 3x minus 3, and keeping up at x minus 4, x plus 2 squared, as so. Uh, then I can assert quite easily, since it's in factored form, that there's going to be zeros at minus 3, 0, multiplicity 1, 3, 0, multiplicity 1, 4, 0, multiplicity 1, and minus 2, 0, multiplicity 2. Where the multiplicities are given by the corresponding exponents, right? So everything's 1 here, so that's why you see 1s for the first 3 zeros. But since there's a 2 here, I have to bump the 0 at minus 2, 0 to 2. Okay. Next, I want to determine the y-intercept. By definition, this is just evaluating when x is equal to 0. So I put 0 in for x, I get 0 squared minus 9, 0 minus 4, and 0 plus 2 quantities squared. Simplifying, this is really equal to minus 9 times minus 4 times 2 squared. So I have 36 times 4, which is 144. So your y-intercept is at 0, 144. Okay. And for the third one, the third question for this problem, I would like to determine the end behavior. And remember, end behavior deals with the leading term. So let's try to find that. Remember, the leading term you can find pretty easily by taking the leading terms of each uh, factor and then multiplying them together. So your leading term here will be the product x squared, that's the leading term here, times x, leading term here, times x squared, right? You take into account the power as well. So I have 1 times x to the fifth. So since 5 is odd and 1 is larger than 0, you expect to have positive odd end behavior. So falling on the left to negative infinity and rising on the right to positive infinity. Okay, so that's number one. Number two, given a rational function, I want to ask you a few things about it and then sketch a graph. So to do so, let's first think about what we have here. Um, so the first question is to ask for domain and range. But we know about rational functions that we have to think about discontinuities first, right? So asymptotes and wholes. And that's why I suggest we do the second and third parts first, right? So in order to determine those, let's first factor this out. This function is factorable, and factoring is, of course, the first thing that you should do in any problem. Um, so if I factor the top, I get 4 times x minus 16, or x minus 4. On bottom, I get x times x minus 9. And I can cancel out the x terms to get 4x minus 16 over x minus 9, as so. But when I cancel these x's, I'm assuming they're not equal to 0. And remember, whenever you do this, whenever you're canceling the factors on top and on bottom, you have to, this is by definition the presence of a whole, right? That means we have a whole at x equals 0. And remember, we cannot divide by 0 because, or 0 over 0, because you know, 0 over 0 is undefined, right? Can't have it be. That's why there is a presence of a whole. So since this whole is only a discontinuity at one point, we can actually remove it because the limit still exists at that particular point. It's just that that point is not defined. So I can say that there is going to be a whole at x is equal to 0. And so to find the y-coordinate, you simply set x equal to 0 in the factored form. Okay? So if I do so, I get 4 times 0 minus 16 over 0 minus 9 minus 16 over 9 minus 9 is just 16 over 9. Okay, so my whole coordinates is at 0, 16 over 9. Okay? Okay, to find the horizontal and vertical asymptotes, we take a look at the factored form, see what happens. By definition, the VA can be found by setting the bottom equal to 0. So x minus 9 equal to 0 implies that the VA, there's a VA at x equals to 9. And my HA is given by, well, let's see. Degree of the top is 1. Degree of the bottom is 1. So they're equal. So the ratio of the leading coefficients is going to be my HA. So 4 over 1. So 4. All right. But since we have a non-zero horizontal asymptote, we have to check if it intersects, or the function intersects this at all. Remember, you can never intersect a vertical asymptote, but you can intersect an HA. And it's non-trivial to check, so let's go ahead and do so. All you have to do is set your factored form equal to the HA and solve to see if there's any intersection. Okay, so if I do so, x is equal to, let's set the function equal to the vertical or the horizontal asymptote and solve. So this implies that 4x minus 16 is equal to 4x minus 36. So if I can cancel out the 4's because with subtraction, and I imply that minus 16 is equal to minus 36. And this is clearly not true. I got a contradiction, so we can assert that there is no intersection of the HA. The function does not touch the HA, and the function does not touch the VA. Okay? This is important for us because now we can define the domain and the range. Right? The domain is where all the x values can be on a graph. So it takes into account the discontinuities of the whole and the VA. Since I have a whole at x equals to 0 and a VA at x equals to 9, my domain will be everything but those 2 points. So my domain is minus infinity to 0, union 0 to 9, union 9 to infinity. Meanwhile, my range is found by the same way. Okay, I look at my whole. I see that I cannot be at 16 over 9 or at 4. So I take all the points on the real line except for those 2 points. So you get minus infinity to 16 over 9, union 16 over 9 to 4, union 4 to infinity. So, okay. The fourth question, you want to find the x-intercepts and the y-intercepts. To find the x-intercepts, you set the factor form equal to 0. Solve. So 4x minus 16 over x minus 9 is equal to 0. Implies that 4x minus 16 is equal to 0, which implies that 4x is equal to 16, so x is equal to 4. 4, 0 is my x-intercept. As for the y-intercept, by definition, that's when x is equal to 0. But as you look up here back to number 2, you have a hole at x equals to 0. So there's actually no vertical, or there's no y-intercept because that's where you have a hole at. Right? By definition, the y-intercept is defined when x equals to 0. But since I have a hole here, there is no x or no y-intercept. Okay. So you can say no y-intercept. So now we have all the tools that we can graph. So let's draw our axes. As so. Label the points that we have. So I'll call this 4, 0. I have a hole at 0, 16 over 9. So 18 over 9 is equal to 2. 16 over 9 must be a little bit less than 2. So if this is 2, I have an open circle. That's how I denote a hole. 0, 16 over 9. And I need to draw my asymptotes as well. So say that this is about x equals to 9, my vertical, or yeah, vertical asymptotes. My horizontal asymptote is at 4. And to graph this, well, first we know that the holes are removable, so but these 2 points like have to touch each other. And also we use symmetry. So if I check this, remember, to graph these rational functions, you're either superimposing the image of the graph of 1 over x, if it's symmetric about the origin, or you're superimposing the image of 1 over x squared, where it's symmetric about the y-axis. And you can check this by substituting in minus x into f. Okay? If you do so into this, you can see that 4 times minus x and minus x, you'll get symmetry about the origin. All right, the negation will happen. And so I choose to superimpose this image here. It's going to be positive, like so. And then the right half will be like so. So this image will go on the left half, right here. And this image will go on the right, like so. Okay. And you want to draw these to exhibit the graphical properties of an asymptote. Remember, they get closer and closer to the asymptotes like magnets, but they never actually touch. All right? They never actually touch. But we can go over to Desmos to see what happens. So let me go through Desmos and plot our function. 1 second. X squared minus 9x minus 16x. X is equal to 4 and no, x equals to 9 and y equals to 4. Okay, so if I share my screens, this is what you should see for the graph, right? So yeah, I have an intercept at 4, but then as I cross my y-intercept where it should be, you can see that it's undefined. That's the presence of a hole. And of course, the blue line, that's x equals 9, that's the vertical asymptotes. The green is the horizontal asymptotes. You can see that No matter how close or how far you zoom to the left or the right, it will never actually cross. And that's what we concluded in our handwritten work. Okay? But yeah, this is the shape of the graph, and you can compare this to the graph of 1 over x, right? If I hide this once for a second, you can see that the overall shape is symmetric about the origin. And we found that by simply substituting in f is equal to minus x. You get that. So yeah, you're either going to have this shape on the left or right half of your graph. That's what you see here. You see how similar it looks. Or if your graph is symmetric about the origin, you're going to have this shape right here. Symmetric, or sorry, if your graph is symmetric about the y-axis, you're going to have this shape right here. So f of x is equal to f of minus x. Okay, good. All right, back to the practice exam. Let me share my screens. So, going on to problem 3, we're now doing the stuff with logarithms now. So, yes, number 3 is I want to use expanding logarithms to, or using the rules of logarithms to expand out this one logarithm as much as possible. Okay, so first of all, we can start with seeing that I have a division. So automatically I think to use quotient rule. So let's do so. I can split this up as log 3 of 27x, x squared minus 4 squared minus log base 3 of 9x squared. Yes, so I simply just use the quotient rule to get rid of to split the numerator and the denominator up into a subtraction. Now, I can see that I have a product of 3 things here. I have 27, x, and this quantity right here. So I can split it up using the product rule. Same thing here. I have 9, and I have x squared. But be careful, this minus sign is non-trivial. This is actually minus parentheses this. Minus parentheses log. So wherever any expansion you do here, you have to distribute in the minus sign. So we have to be careful. So let's see how that works out. We get log base 3 of 27 plus log base 3 of x plus log base 3 of x squared minus 4 squared minus log base 3 of 9 plus log base 3 of x squared. Okay, right. And simplifying further, now this is the point where we either compute out the logarithms if we can, like these number logarithms you can simplify, or you use the power rule to put any exponents you see in the arguments to the front. So that my final answer should be given by, so log base 3 of 27, I ask myself, how many times do I raise 3 to what power to get 27? It's going to be 3. 3 cubed is 27. Plus log base x, so log base 3 of x, plus 2 times log base 3 of x squared minus 4, minus what? Log base 3 of 9 is just 2, minus 2 log base 3 of x. Okay. Let me go further, even more. We notice that x squared minus 4 is x plus 2, x minus 2. So you can split this up using another product rule. And combining like terms, we have 3 and minus 2, log base 3 of x, and minus 2 log base 3 of x to get 1 minus log base 3 of x plus 2 log base 3 of x plus 2 plus 2 log base 3 of x minus 2, like so. So your final answer is actually given in what's underlined in red. Okay, that's so. All right, problem 4. We expanded a logarithm in problem 3. Now we're going to go backwards and condense. Okay, so you're going to use the product and quotient rules in reverse. So we first notice that I have subtraction. Immediately you should think quotient rule. If I do so, I get ln x squared minus 4 over x squared, or x minus 2 plus ln 5. Okay, and then I have addition. So product rule. So ln x squared minus 4 times 5 over x minus 2. But again, the difference of squares gives me x plus 2x minus 2 times 5 over x minus 2. So the x minus 2 goes away. So your final answer is ln 5 times x plus 2. Like so. All right. 5. I want to solve for x immediately. Same base means I need to set the exponents equal to each other. So this problem really degenerates down to a quadratic. And we know how to solve these, so we'll go really quickly. X squared minus 3x, or minus 2x. Or no, this is minus 4x. My bad. So you have x equals to 0 or x equals to 4 if you factor properly. And yeah, these are your two solutions, right? E to the x is continuous, so, and as an exercise, you can check that these are both indeed solutions. 6, I want to solve for x. So again, in this case, notice that I have a log base 2 term on both sides, just only one. So if I only have one log base 2 term on both sides, I simply can just set the arguments equal to each other. And this is also just another quadratic equation to solve. It's 3x is equal to 0. So x is equal to 3 or minus 3. So we have to check, right? So one can show that x is equal to 3 or x equals to minus 3. But if you put minus 3 into the right-hand side, for example, you get log base 2 of minus 3 plus 3, which is log base 2 of 0. And that's undefined. Remember, the logarithm domain is only for positive numbers only. No 0, no negative numbers. So you have 0 or negative numbers, that's going to lead to an extraneous solution. So x minus 3 is extraneous. And now we can check um, if, actually, what did I say? Oh yeah, x equals minus 3, but oh, this is supposed to be x equals 0. And we can check now that if I have x equals to 0, then on the left-hand side, I get log base 2 of 0 squared plus 4 times 0 plus 3, which is equal to log base 2 of 3. Okay, on the right-hand side, log base 2 of 0 plus 3 is just log base 2 of 3. So x is equal to 0 is your solution. Okay. Number 7. I have two logarithmic expressions that I would like to solve or evaluate. The first one, you can write this as log base 5 of 1 over 5 squared, which is equal to log base 5 of 5 to the minus 2 using your reciprocal rule. And then by your inverse rule, these cancel, and this is just minus 2. The second one, if I don't write a log base, I mean log base 10. And 0.01 in decimal form is nothing but 1 over 100. But this is nothing but 2 times log base 10 of 1 over 10 squared, or 2 times log base 10 of 10 to the minus 2. So again, by your inverse rule, you get 2 times minus 2 is minus 4, like so. Okay. Problem 8, it's going to be a application problem. All right, so a savings account grows according to this model A of t, and we want to see how long it takes for the balance to quadruple in value, the initial balance. We want to leave our answers in the form of an exact form. So no decimals, you just leave it in exact form, so a logarithm. So what does this look like? Well, first I say how long. So instead, I'm not solving for money, I'm solving for time t, right? So that's the main question. And initial balance means I need to first find what the initial balance is. Initial, in this case, always means t is equal to 0. So if I solve for t is equal to 0, that's just 12,000 times e to the 0.024 times 0, which is just 0. And anything to the power of 0 is just 1. So a of 0 is 12,000. I want to see how long this takes to quadruple, so I want to see how long it takes to reach $48,000. So all I have to do is simply set $48,000 to the function and solve for t. Okay, so this is just an exponential equation. First, I divide both sides by the number. So you should get 48,000 divided by 12,000. That's just 48 divided by 12, which is 4, is equal to e to the 0.024t. And now, in order to recover that t, to drop it from the exponent, you have to take the natural logarithm of both sides, right? Remember, natural logarithm is log base e. So the log base e and the e cancels, leaving you with ln 4 is equal to 0.024t. So dividing by 0.024, you get that t is equal to ln 4 over 0.024 time. So there's no units here, so you don't have to worry about units. You can just box this answer, like so. And then the last problem, we're just going to be asking a few questions about a logarithmic function and then graph them. So I have a function h. I want to determine where the x-intercept of h is. So you set h equal to 0. Minus 1 minus 2 is equal to 0. Or log base 3 of x minus 1 is equal to 2. And in order to undo the log base 3, you raise both sides to a base of 3, corresponding base of 3. So that by your inverse rule, the left-hand side cancels, leaving just the argument. And the right-hand side, you get 3 to the 2, which is 9. So x is equal to 10. So 10, 0 is my intercept. My VA is given by the horizontal displacement. I'm moving right 1 units, so my VA is going to be x equals to 1. And so to graph this, I plot my axes, I label my axes, I label my vertical asymptote at x equals to 1, my x-intercept at 0, 10, or 10, 0. And now I have to think about another point. So you can think about setting uh, about making the argument powers of 3. All right, so what x value will give you a power of 3 and one other point on the function. So to graph one other point on the function, you want to think about setting logarithm base 3, this x minus 1, the argument, equal to some power of 3. Okay? Some power of 3. Why? Because if you set it equal to some power of 3, you can easily calculate the logarithm base just by asking yourself, what power do I raise 3 to get me the argument? So powers of 3 are going to be 1, 3, 9, 27, and so forth, 81. So let's set this equal to 9. Actually, no. Yeah, let's set this equal to 9. Not quite. So 9 doesn't work, right? So now you get 10. So we can think about setting it to 3, I guess. So x is equal to 4. So what happens when x is equal to 4? Well, now logarithm base 3 of 4 minus 1 minus 2, that's just the function evaluated at 4. I get logarithm base 3 of 3 minus 2. So 1 minus 2 is negative 1. So I have a point at 4 minus 1, which is somewhere right here. 4 minus 1. Connect the dots like this, and that's your logarithm shape right there. Okay? And to compare with the graph on Desmos, I always suggest you guys to try it for yourselves to validate your answers on Desmos. We can plot the function log base 3 of x minus 1 minus 2 and the vertical asymptote at x equals to 1. You can see that it never crosses. And there's your x-intercept at 10, 0. And there's going to be a point at 4 minus 1. Okay? So again, to plot an additional point, all you have to think about is setting your argument equal to a power of the log base, and then solving for x, and then using that x to go back and run it through the function to see what your y value is. That's how you find another point or another 2 points. Doesn't matter. But yeah, that completes the practice exam. So study well and good luck on your exams.